first of all, I want to thank the organizers for the opportunity to speak. And I will present this very interesting topic of extreme R-process enhanced stars in the Fornax dwarf spheroidal galaxy. So let me get directly into it. First, a bit of background what a dwarf spheroidal galaxy is. So here on the left, you can see a sketch of the Milky Way with the thin, the thick disk, and the bulge, and the halo. And we have like galaxies, the dwarf spheroidal galaxies, satelliting around the Milky Way. So here on the right, you can see basically an example of several of these dwarf spheroidal galaxies where we have the galactic plane here at 0. And during the talk, I want to focus on the Fornax dwarf spheroidal galaxy. And these galaxies are interesting because they have been proposed to be the birthplace of extreme enhanced R-process stars, for example, in the case of Reticulum-2. And they are also interesting because each of these galaxies has its own chemical history. So in 2020, we basically reanalyzed 380 stars from these different galaxies. So now you can see barium abundances and europium abundances here next to each other, and each panel is a different dwarf galaxy. And we can see, for example, this extreme enhancement in Reticulum-2 here on the bottom, where we have extreme R-process elements at low metallicities. But during this talk, I want to focus on these 3 stars in Fornax that are also enhanced in europium, but at higher metallicities compared to these reticulum stars. So basically what you can see here on the bottom is the same figure as before, but now a bit larger. And we can see the Fornax stars here as green dots, and the Milky Way is the background gray dots. And the 3 enhanced stars are basically these orange stars here. And if you look basically not at the square bracket notation, but at the absolute abundance notation, you can see that these stars, at least 2 of them, are extremely enhanced in europium. And we were unable to find any other star that has a larger europium abundance. There's only one star, this SCMS 982 here, which has a comparable europium abundance, which we take from literature. Yeah, so if we look at the spectrum, okay, sorry. So basically, let's look at these 3 stars, these orange stars, the black one, and the reference star here. It's also from Fornax, the red star. If we look at the spectrum of these stars, we can see the enhanced stars here on the top. So this is shifted. The reference stars here, and we have the SCMS star, which is here at the bottom. So we can already see from the spectra itself, because all of them have similar stellar parameters, we can roughly compare the europium abundance, which you see here, the absorption line, and you see that the enhanced stars have a deeper line compared to the reference star, and it is similar to the SCMS 982. So this just as a proof of concept. And we can do the same for barium. And there you actually see that the enhanced stars have similar barium compared to the reference star here in red. And for sure less barium than the black one. So this black star is proposed to be S-process or I-process enhanced, whereas our stars, as I will show later, are R-process enhanced. What is very nice if you have high absolute abundances is that your line will get deeper, and therefore you will also be able possibly to measure elements that you would otherwise be unable to detect. So we searched for other heavy elements, and actually we found lutetium and one absorption line of lutetium that you can see here. And we were able to measure this abundance, and it's actually the first detection of lutetium in a dwarf spheroidal galaxy. Here you can see basically 2 spectra. One in black is shown without any lutetium enhancement, so with basically no lutetium. And you can see a red one where we synthesize lutetium on this spectra. So now if we translate the spectra to actual abundances and compare to another R-process star, we can see that these stars basically follow quite nicely an R-process pattern. And let's look also at other elements. We can see, for example, for magnesium. So again, these green stars are Fornax stars. and the gray background is the Milky Way. And as Andreas has mentioned in the second talk already, dwarf spheroidal galaxies can have a different magnesium content. And also the enhanced stars here in orange follow perfectly the Fornax trend. And this is a proof that they really belong also to Fornax. What's also interesting is if we look at zirconium abundances, again, Milky Way and Fornax, we can see that these outlier stars that have a lot of europium also have a lot of zirconium. So whatever enriched these stars in europium may also have enriched them in zirconium. But now that we have the abundances, what can we learn about these stars? So it would be super nice to distinguish between, for example, different production sites of R-process elements, for example, neutron star mergers or magnetorotational driven supernova. So these just as examples. And ideas to distinguish between them would be comparing elemental ratios, looking at the amount of ejected R-process material or delay times. So let's look first at elemental ratios. So here we show the elemental ratio of barium versus europium. So barium is traced for the S process and europium is traced for the R process. And even when this figure looks very complicated at the beginning, it's actually not so complicated. So let me explain it very quickly. We have S process models from the Fruity database, which we put here as lines. So they produce these ratios. And we have obviously the stars here as dots. And on the left, we have different R-process scenarios with different nuclear physics input. So you can see basically this one bar is the result of one theoretical simulation with different nuclear physics input. And we can see that we compared neutron star mergers, neutron star black holes, several disk models, and magnetorotational driven supernova. However, within the uncertainties, they are still quite large. So it's basically impossible to distinguish any of these scenarios from with the current uncertainties. So let's come to the next one. So we thought, okay, how much europium would be necessary to enhance these stars from the average europium abundance in Fornax? And is it even possible that this could be one event, or are there more than one event necessary? So to calculate this, we we also need the gas mask, how much, so where we mix into the europium. And this we took from Mack et al. 2020, which is this formula. And then we can just straightly go on and calculate how much europium we would need. So finally, we end up at the value between around 10 to the minus 5 to 3 times 10 to the minus 4 solar masses of europium. And yeah, so the question is, how does this compare to the different scenarios? For this, let's look at this figure again. So we have the gas mass on the x-axis in logarithmic space, and the europium log epsilon. And for example, for one of these stars, we have a log epsilon of europium that is this line with the arrows. It's the dashed line. Then we make some estimates for the explosion energy, and then we get a certain gas mask we mix into, which would be this. So our star should be enriched by an europium mass that lies into this rectangle. And if we compare now to simulations, so the actual mass that you get from theoretical predictions from europium, neutron star mergers lie around 8 times 10 to the minus 5, which is this black line, or even lower. And if we look at magnetorotational supernova, it's even lower and right at the edge of this box. And we can also compare it to previous estimates, for example, for reticulum-2, which would lie between these two lines. So actually in agreement with what we have calculated. So it's pretty difficult to distinguish between these scenarios. However, we can clearly say that from this, that it's perfectly possible that it's only one event that enhanced these stars to their extreme enhancement. So last, let's look at timescales. So here on the left, you can see basically the star formation history of Fornax. As I said at the beginning, these are stars that belong to a dwarf spheroidal galaxy. And this dwarf spheroidal galaxy actually has a very interesting history. And you can see here these lines. So these bumps correspond to actually increase star formation in this galaxy. And if you look at the age of the stars that you can get from the color magnitude diagram, they are around 4 to 5 gigayears old, which corresponds to exactly one of these increased star formation episodes. Which also means that possibly the R process event is connected to this star formation episode, which is quite interesting. And which tells you basically that there's possibly a short delay time of this event. However, there are also this also does not really distinguish between two events, because of course magnetorotational supernova are thought to happen quite quickly, but there are also statements in literature that also most of the neutron star mergers will happen in active star forming environments. But nevertheless, we learned from these only 3 stars a lot from the R process event itself. So with this, let me come to my summary. So I showed you stars that have the highest absolute europium abundance that was measured so far. With this, it was possible to also detect other heavy elements that are usually very difficult to detect, like lutetium. To compare the zirconium, we also derived zirconium abundances for basically all Fornax stars that we had. However, if we compare to elemental ratios, it's pretty difficult to distinguish between different astrophysical host scenarios. And yeah, the ejected R process material is in agreement with a single R process event enhancing these stars. And finally, we connected the star formation history of Fornax to the age of the stars, which also gives us more insight into the R process event, into the property of the R process event. And with this, I want to thank you for your attention.
Thanks a lot, Moritz. I really like your talk. Thanks a lot. And yes. So it looks like that, I mean, it was too exciting, this talk. So also the one before, of course, so not many questions happen to be in the chat, but let's see if someone is raising her hand or his hand somewhere. Otherwise, I will start again with I have a question myself. Do you expect to see some similar events or weird or extremely rich star also in some other dwarf spheroidal, or do you expect it to be just a rare effect in Fornax?
Actually, it's an interesting question, because most of the stars that you can see here on the upper left are actually stars that are either from dwarf spheroidals, so like this COS 82 is from Ursa Minor, and also these SCMS stars from Sculptor. But the stars that are shown here that are not from a dwarf spheroidal are actually show indications that they got accreted to the Milky Way.
Yeah.
So I would expect that there are, of course, more stars. And if these claims in literature are correct, that most of the neutron star mergers happens in active star forming environments, I mean, then you can already constrain a bit where you should look. Yeah.
You constrain the R process event or the... Yeah, excellent. I see now a hand from Andreas. Yeah. Please go ahead with your question.
Thank you. Very nice talk. Interesting. So from my perspective, you're moving a science that is usually done at quite low metallicity to a regime that is considered moderately low metallicity. And this has some modeling consequences. I mean, on the one hand, the lines become stronger, as you said. So you see more lines, you can detect new elements, but for the traditional lines, they become much stronger. Their line formation will be moved to shallower optical depth, where maybe your 1D model atmospheres are not as good. Have you explored the interplay of these effects sort of from the 1D, 3D perspective?
I mean, we did not really explore this in detail. I mean, we just looked at some NLTE correction grids for some of the elements. But for example, we did not do it for iron, which would probably be necessary. So there's still a lot of improvement that can be done. But still, I do not expect europium, for example, to be so much affected. With zirconium, it's probably something different because we're also measuring neutral zirconium. But still, I mean, the qualitatively statement that that these stars are enhanced over the general trend, I think is quite robust. So you cannot.
Yes, no, I can buy that, absolutely. And I was just wondering, because you know it's the shallow optical depth, it's the temperature gradient in the shallow layers that is the biggest difference when it comes to the T-TOR relations between 1D and 3D models. And this is where many of your lines may end up. So it's not just a matter of non-LTE, it's unfortunately probably a matter of 3D plus non-LTE that gives you in the end, the right abundances. But yeah, I mean, I think probably your conclusions are not severely affected by this.
Yeah, I totally agree that probably the exact numbers are quite uncertain.
Yeah.
For example, the ejected European mass, that's for sure.
Okay, thanks. Chris, do you have a quick question for?
Yeah, just really quick. I mean, I completely agree that I think you're safe here, because if you're going to have a special explanation for the strong europium lines, you've got to do the same thing for other features as well. And so I think mostly a differential analysis is actually pretty strong.
All right.